Okay, I'm going to dare do it immediately. Welcome to podcast 39, my weekend attempt at getting this podcast done and acknowledging TechSmith's AI's capability of finding out that you're critiquing them and shutting you down continuously or locking out certain features like sound in the last attempt. The last one, I started the critique and I said I'm actively looking for something else, and I can't believe I've gotten this far. So, never again. I am looking for something that does not have an AI attached to it, so that it can't self-decide that to knock your recording out. So in any case, enough of the rant. I am now 16 hours into doing this podcast. I will get through it this time. We are going to cover the EMPATH ECMS continuous monitoring systems capabilities and how to set it up. So I'm going to cover a little PowerPoint first, and we'll see how poorly my voice syncs by the time this is done, if there's sound at all this time. So I did a perfect version 2 iterations ago. So I'm a little frustrated with an update to a software that used to serve me quite well. So let's get into the ECMS, and this is why we do not have AI built into the EMPATH system. People make decisions. That's it. Machine learning, fine. Well, actually, AI is machine learning. But it's heavily biased based on whoever's programming it. So here's the data collector. It's the one I use this one here is my backup unit now. I have one that has the vibration analysis built in for the study we're doing for comparing energy losses and calculating energy losses using vibration data. As you notice here, this is a 13/8 panel, and we're at the back of a relay. So I'm going to talk about that in a minute. But the system itself is designed to connect up directly to up to 1,000 volts phase-to-phase AC or DC. That includes the E-plugs. Anything above that, you need to go off of a relay, and you need to use a separate type of CT for the current for grabbing current than the existing CT. Okay, that's the only way you're going to get accurate data, because you need to have a system that does millivolts per amp, which is what you use for oscilloscopes and everything else. So in this case, your regular current clamps that are used on oscilloscopes, scope meters, your whatever, and power analyzers, all put out millivolts per amp. Okay, especially if you're going to convert anything over to a spectra. So we have that coming in, and then voltage, of course, right? So, and then that connects up and it's powered by your laptop. So that's a different type of system. However, doing the same thing, because it's the same card and it's the same software that we use with the continuous monitoring system. Now, this is the older one. This one takes in up to 32 machines worth of data from E-plugs. So the E-plugs and the A to D card and the multiplexer and the signal conditioners that are built into the box are all connected via Ethernet. And so the output from the E-plug is all under 10 volts. So that comes out from the E-plug to here, and this uses exactly the same system. Same software, same needs, and everything else. You can either use, and I'll show you in a couple of examples of our gateway-style computer with it, or you can spin up a Windows-based virtual PC, or you can control it directly from a server, as long as it's Windows-based and you can connect through the service to these. Each instance of software handles up to 100 boxes, and then each box has either a single channel or 32 channel. One of the cool things about this is the ability, as we talked about before, to see the entire powertrain, incoming power, electrically and mechanically, including bearings, all the components within the motor, including lubrication issues, through a coupling, including the belt. And yes, you can see your driven equipment through a belt, through a coupling, including a flexible coupling, and everything else. I've had people attempt to say that you can't do it, so I went back and I proved it out mathematically as well, because we've been doing it since 1989. Accurately detecting driven equipment to the point now where the wind industry has included ESA as part of the powertrain playbook, gearbox in particular. So we can see every gear, every bearing, everything else. So we'll talk about that briefly, but we're going to talk about the continuous monitoring system mainly. Well, going in, just to give you an idea, with the e-plugs and all of the hardware, including the software, which has no annual fees, you're at under $2,000 per machine with a box like this. The e-plug is the smallest one in the market. It takes and converts everything over to low voltage and current. It is patented by Framatome, and it can take up to 1,000 volts phase to phase, all the way down to a few millivolts, and then put that out to the system, and it's automatically figured out by the box. This is an ECMS E1, which is a single channel version with the e-plug built in. Now, the first one, the ECMS 1, we call it the O1 now, but did not have the e-plug built in, and just figured we had the room, put it in. So takes up less space now, 5 by 5 by 3 inches tall. So here's one. We do a lot of these for power monitoring and incoming power. All of them will do motors, transformers, DC motors, synchronous motors, machine tool motors, you name it, we do it. So we have this set up. It takes in the data. This was a location where we were originally going to mount it on the utility meter, but there was an error made, and nobody called the utility. So we ended up going in, pulling the fuse block here, wiring everything on the secondary of the fuse block, using the control transformer power, which put out 5 volts to power this and everything else, and basically had it installed in about 30 minutes or less, plus an output cable to connect up outside to gather data as well. So all of that was set up in a matter of no time at all, and monitoring incoming power, and it's been there for about 4 years. Next one is a recent one. You may have seen me post this before. I don't get a lot of good pictures of this because of where they're located. This is nice because it doesn't show who has it. So in this case, I have 2 of the PCs that I was talking about. They transmit their data via cellular modem, 2 ECMS 32s. There's the cables coming in. Ethernet has a range of 105 meters. In a recent presentation by somebody else, they said 105 feet. That's incorrect. It's meters. That means well over 300 feet. So 320 feet. After that, we see a minor degradation. We have installed as far as 1,000 feet away, and that is length. So these come in and they're connected up, and then each one goes out. You can see they're nicely labeled by the machine. So they plug in, each of the locations is labeled. Each of these is independently managing the box, keeping it local. So the data resides here. It's kind of an edge system. In addition, a second set of data can be saved to wherever you want. So and as a matter of fact, for this particular application, you don't need to use our cloud. You don't need to use whatever else. It's a rules-based system, meaning that all of the algorithms are built in. There is some machine learning to it. I'll show you that in a little bit. And then, of course, we have layered softwares that all come with it that allow time to failure estimation and things like that. So all of that exists. You can put it on the cloud, you can keep it locally, you can have it on a local PC, you can even just remotely log in and look at it periodically, whatever you want. It's pretty flexible. This one is outside. To give you an idea, temperature range, this area here over the winter, which is in upstate New York in the mountains, was minus 30 centigrade. So it got to see some pretty cold weather. The nice thing is the remote PC is a fanless PC, so it keeps it warm in the winter, and then the box is set up and selected, and how we laid it all out was to allow for pulling in an exhaust of heat that allows it to stay relatively cool during the summer and can hit 70 degrees centigrade inside here before there's any issues. All the components are selected for that. Now, you don't need to buy a box like this. Some people do their own thing. We came up with this because of an installation where we said, you know what, we need to offer to have it done, and that way we can also have disconnects. This came in handy at another site where they were having voltage issues, and we'd had the circuit breakers trip a couple of times so far, but it protected the whole system. This list is much longer now. I'll show you that in a little bit. It'll even include trending the energy and emissions costs and values now. So all of that data is now available in the system when it comes out. For a quick view of how it can be set up, because it's flexible, this edge computer here can be your spun up virtual PC, your server, a computer, whatever you want, as long as it's Windows based. We put an edge computer in there. They're inexpensive, so we don't put a big cost adder on anything. So you get it. We don't pre-install, unfortunately, anymore because Windows 11 and Microsoft wanting to know who does what. So we don't want to set it up under our accounts and hand it over to you. Some places will actually want to re-image the drive, so we allow that and so on. The Microsoft software we provide on a USB that pulls the data and presents it in CSV format because the type of database, it's an Access database that's presently used. That'll be updated in the near future. It does have email alerts. It does can connect whichever way you wish. And in one of the things that we do, if we're monitoring it, we'll have a cloud system and the ability to access it with the software. Basically, the security is you have to have a copy of the software. And then in the end, the EMPATH software kind of keeps an eye on everything. And it's the same software as for data collection. Let's see, automatically, it doesn't tell you a range or this might be the condition or it might be a fan or it might be the air gap or something. It actually tells you what it sees. If it's even right down to if it's a bearing, it'll tell you the component of the bearing. All kinds of stuff that we test and so on. And I know this is sounding a little commercial. Scheduling, we're going to show you here shortly. I'm going to skip that. And then there's another capability where you can create this type of text file. You put it in with the cFramatome folder along with the calibration file, and it'll analyze your, those components you put in the system and allow you to make adjustments to them and everything else, and alert and alarm you on it. Green instead of yellow or red, just because, colorblind. Not me. And then if you are working with us, we do dashboards. Dashboards can be for groups of equipment with little dots saying red, yellow, green by machine, laid out however you want. We don't use the Microsoft system. We use somebody else's. We found that to be secure, as secure as you can be. And it provides whatever data, and you can see this one is for energy monitoring, and those are the cycles by week and all kinds of other stuff. The built-in trending and other capabilities, I'll show you that when we get into it, is also there. And then this is just some applications. This is the why we set it up. Somebody put this together. It's in a metal box. They put the cover on it. It caused a Faraday cage, and the antenna for the cell modem stopped working. This has all of the alerts, alarms, forecasting, all kinds of stuff. Like I can even forecast future energy based upon expectations from this in order to see where we are months out, that kind of thing. The other extreme than northern New York is the Mojave Desert. That is not a painting. That is actually a picture I took in the yard of the wind company of the towers that we were monitoring. So these are in there, and it'll see some pretty good temperatures in the summer, pretty cold temperatures at night in the winter. But the software will do continuous monitoring and will also show a verbal typed, this is the condition, instead of bars where it says, well, maybe this, maybe that, based upon some stuff somewhere else. Nope, it's rules-based. It's right there. Yes, no. You can change the rules if you wish, but that's about it. So that takes care of the presentation. I just did it in half the time I did it the other time. So let's take a look at a continuous monitoring application. So first I'm going to turn this off so we can start from scratch. I'm going to have to pause when I turn it back on, just because of the software. It's probably going to mute my voice now. Again. Punks. Do it again, punk. Okay, so when I come in, right now it's showing a board there. Let's go ahead and I am going to get rid of the board. And I'm going to show you exactly what we're going to do. So remove the board. Okay, so here we are. If I'm doing data collection, it automatically pops something up here. If I have something like what we're doing, this is web-based. Here's the ENet. It's going to call up that board. Poof, there it is. I'm going to add it, and you see it calls it board 0. Now, I have put it in as board 50 into the system. Let's keep doing that. So we're going to change the board number, and we're going to make it board number 50. And that's just for the purposes of showing you the data I've already collected. So we're going to say OK to that. Now, one of the things we ran into earlier when I did the last one as well is while I'm doing this recording, the recording software is taking up so much of the resource that it really messes with the flow of the data coming in, so the data is not as good as it should be. That means, by the way, that you want to really pay attention to how you're doing it and what you're doing it with. Hence why we try to keep a clean computer on it, or if you're spinning up the virtual PC, make sure it's specifically for this type of equipment. Once I have that there, the rest of this I might use if I'm doing troubleshooting. But once I'm done, I can get rid of it. And then I open up the software. A lot of the stuff I've pre-entered, how many ever attempts ago at doing the podcast. I'm not going to zero everything out and start over again. There we go. I'm on the other screen, so here we go. So what I did is I set up a COM folder. The COM folder, I didn't have to set up anything underneath. That's going to be set up by the software. And then under the Framatome folder, I set up a folder called temp. Now this is where I'm going to put my nameplate data. It is going to update to here. So this is the same data as in here. and this is where it's doing that. The data I have here, this is the ones where I manually ran it to make sure everything's all right. And you can see the lengths should be 48 seconds. They're 0, 4, and 5. Well, that was because I was recording while I was doing it, and it really messed with the flow of data coming in. Too many inputs, I guess. So in any case, so we'll get started. So the first thing I need to do before I do anything else is make sure that my setup is right. So I come in here, I do the setup, I make sure that I don't have, sometimes it'll be a string of numbers. That is not the calibration file. The calibration file should be ECMS, depending on the type of ECMS you have, or in the other cases you see it showing as serial number. Those are for the actual boxes. Okay, so we have that. Whichever you wish here, check everything there. Next one is if I'm just installing the software, it usually shows this. Make sure it's at 65536. Leave the A to D card error message unchecked, uncheck calibration warning. All that's going to do is put up a button saying acknowledge me, and when it does that, it stalls the software. Make sure 65536, and here check all the boxes except for unidentified peaks. Again, it'll toss up a checkbox. You can update to your kilowatt hour cost, and your carbon emission should be for doing correction, so it's the reduction value. Right now 0.699 metric tons of CO2 per megawatt hour, which is how the software is going to calculate it, is the national average. Now, if I was inventorying per ISO 51000, then I would be using a different number. That's actually based upon the base loading. So put that in there, leave this all the way it is. These are all defaults there. Make sure everything here is checked, especially default low frequency sampling rate. These allow you to go in and change the color code for the different channels. Channel 1, 3, and 5 are current. Channel 2, 4, and 6 are voltage. Channel 11 is calculated. Channel 7 and 8 are on data collectors. Channel 9 and 10 are not used. This one here, you can set all of your alerts and alarms and change some basic settings. So one of the things that I do recommend you change is the minimum load to take a rotor bar call. I'll set that to the minimum, which is 5%. And then current deviation, I'll increase that to 10. 5 is going to give you a lot of false positives. And when I'm done, I'm not done, because I still have to go Control Alt Enter to get my hidden folder, and I need this in order to set my communication folder, which is that COM folder there. Select that, click Happy, then it's set. Update this. I usually say update it to 999. That's 1,000 basically, and then I might switch this to like 25,000, but I'll boost it back down to 10,000 if I come in here and make any changes. Allow a second copy allows me to take whatever data I'm collecting and save it also to another location, whether that be the computer, a synchronized folder, a cloud folder, whatever I want that can save that data somewhere else as well. So I get a full and complete second copy. And then I just make sure I have allow a second copy. Disable reboot at midnight. The reboot just means restart the software. That's great if you're doing continuous monitoring remotely, because if anything hangs up, it goes away. There's also a backup part for that as well called Watchdog. It runs all the time. So if the software crashes for any reason, it just restarts it. So basically, I've got systems that have been running for months and months and months, and a couple have been running for years, in which I've not had to do anything. Now, nameplate information, again, just like before, you type in the name, hit enter, so test, and you can see I've got a check mark next to it. hit enter, and then it'll create this. Come in here, make sure all my millivolt per amp stuff is correct, 1, 3, and 5. Okay. And then hit the happy face. Nameplate information goes in. If it's got driven equipment on it, you put that data here. Get this all up to date. It's a 3/4 horsepower, 1800 RPM machine, 230 volts. I do not select VFD, even though I could. It'll knock out some of the stuff that I want to detect. I also don't check these. Rarely will I check any of those, but I normally don't. This one here, I don't really do anything with either. Operation 24 hours per day for this machine. 3 amps. So I've entered in 3 amps. I dropped this down to 0.3. And then from the database here, and looking up the ABB motor, I had 28 rotor bars, 36 stator slots. In here, if I create one of those USR files I mentioned, I can pull it in from here, and if I do that, it attaches itself to this particular machine, and then it'll pull up another tab that I can update the data, my limits, or what components or bearings or whatever else. Bearing information, if I double click on this, it pulls up a selection menu. It has 68,000 plus bearings in it. When I select that bearing, it will put in the multipliers for inner race, outer race, cage, and ball spin. I thought there might be limitations to it till I hit the main bearings on wind turbines and discovered those bearings are even in there. The ignore list is another thing. This is specific to continuous monitoring. I can go in and check off anything I don't want it to detect. Check for sufficient current is there so that if I fall under that minimum current, if I leave this checked, it will just not collect that data and say it wasn't running. If I do uncheck it, there's a chance for errors in data collection if the machine is fully unloaded or off. So I usually don't do that. Going back to here, and plant info just gives me ability to put in information, and then this, whatever I put in here, shows up in the comments and any reports. Now I do put in box 50, which is what we selected. That's the card. And then switch number. So if I've got a 32 channel system, that gives me the ability to select the channel. So 0 through 31 is technically 1 through 32. And then the resolution, which gives me bin size that I'm going to use for making calls. So I have all that. Click OK. Then the next thing I'm going to do before I do anything else is I want this. I can either do it as basically RT, just continuously monitors and just brings in just raw data. It doesn't bring anything else. But the ECMS one, I'll click on that. And if it isn't already in the system, I would have gotten a yellow box that says, hey, you're now added. In this case, it's already in the schedule, so it's asking if I want to remove it from the schedule. No, we're going to leave it in there. So nuke button is not pressed yet. In the Framatome EMP 880 folder, you will have something called sch.exe. I usually make a copy of that and either pin it to the taskbar or put it on the dashboard. See, last thing to notice on here, by the way, is if it's connected, you'll see at the bottom of the screen, you'll see the calibration file number and which board it is. So that one, board 50. So if I go ahead and select the scheduler, see, oh, everything's moving a little quicker now. Maybe the AI listened to my complaining. Okay, so you can see that it's got data already, and just to give you an idea, it's pulling the data from stuff in this COM folder, and it is presenting it. So it's showing me the findings. Now, if I double click here, oh, the red dot means that there's stuff going on. So if I come up here, you can see that press Shift left mouse to reset alarm. Shift left mouse. There we go. So it just switched everything back to OK. If I come in here and I double click it, let's go to the schedule. I selected 5 minutes. I can select basically anything I want. Once a day, which days, whatever. This will be unchecked. I click. Okay, here we go. I click to run the schedule. Now it's not going to start running yet. And if I click on this button over here, it's not going to do anything yet. Until, once I have this set up, I click here, and then I can have it run a quick data set. Now, what I do also do is sometimes I'll go ahead and run a set. I've done it several times already, but I'll run a set and I'll go in, I'll hit F8 so that I get all my phases in line and everything else. I'll show you that next. So if I do this and nothing occurs, now this is actually saving it to the database as well, and nothing occurs, then that means that I've done something. And as soon as this went smooth, I know that it's going to upload bad data because I'm running this recording software in the background. It's cutting out a bunch of data. So, but you can see the percentage increase here. So it's going to look really low resolution because it looks like it did like 4 or 5 seconds or something. Yeah, let's see what it looks like. Told ya. Yeah, not good. Anyways, so we'll look at some good data. But it's going to come up with conclusions and everything else that will show up in the other here. Okay, so as soon as it updates, there we go. It updated, set it back in alarm, everything else. As soon as it sets it back in alarm, it would have sent out an email as well, but I didn't set that up. If I change that location to somewhere else, I do come in here and reset it to the new location. Okay. So let's reopen that up. There we go. So there's my schedule. I did the other thing. I might want to go in here and double click, and I just did way too much to it. So we'll give it a second and do my, sorting out and so on. Double click on it, and there we go. I'll just run a quick one just to show you. So get it up. Showing the waveforms and everything, and then I can hit F8, or I can do this and it'll set the gains, it'll set the order. It's going to give me something wrong because of the way I've got this VFD driven equipment set up. So it's just going to find something and it's going to give me something oddball. But they are actually set up 1, 2, 3 and 1, 2, 3, but it's going to do like 1, 3, 2 and 3, 2, 1 or some such thing. So what I want to do if I do this is make sure that the power factor is the highest level power factor and I get no negative numbers. And I am going to have to pause it briefly. Okay, here's what I was talking about. As soon as it's done, I can retry and try to get these so that I end up with high numbers here. Or in this case, I'm just going to click OK and let it settle in. When everything displays again, you can see there's my voltage there and there's my everything else there. There it goes. Then I have a choice. I can download it or not. But once the gains are set, they're set. So I've already got it set up for continuous monitoring every 5 minutes. Once I start collecting data, this will pop up, and this gives me direct access to that database. Now, here I have everything: inrush currents, inrush duration, voltage, all this other stuff. These are all things monitoring, up to and including any losses, that kind of thing. And then what it does do, let's go ahead and take power. Okay, what it does do as part of this is it will use machine learning and set the tolerances. So basically it learns as it goes, and if things fall outside, it'll do certain things. And it'll also allow me to take a look at the data points. So I do have for each of these, so let's take a look at motor current. Tolerances have been within this range, etc. So all of that is there. That's the alerty thing that's separate. Here's the header information for the machine. Here's the notifications, so that's where I reset everything. I basically emptied this. And here's the report showing everything. So this is a text. This is the text file. And it has all of the findings on it and everything else. That's part of what we pull out and parse the data on to put on our dashboards. So that's as tough as I can make it. You see it's running in the background. It gives me the dates. It does some other stuff. This gives me the ability to call up and do an analysis of the last file that was done. Of course, it's going to lag. Looks like I got some pretty good data on the last one, so we'll open that up real quick. So let's go in here, COM folder, box, and then this is the last data set. Wow, time is passing fast when you're having fun. So here's the data set. Yeah, this actually came out pretty nice. If I wonder what's going on, and you can see pole pass frequencies are dead on there. Big casting void in this little motor. It's awesome because I use it for demonstration of things and everything else. I've got some bearing fluting going on and so on. It's tight enough that it's early enough that sometimes it shows, sometimes it doesn't. There we go, misalignment or unbalance. If I have questions on anything, I can double click. So if I want to see bearing information and see where it would have pulled it, I just double click on it and it's going to pull up all the points for me on any of the screens. And these are just the quickly displayed screens. Okay, so you can see there's the bearing stuff, both in DMOD and up here. I tend to use, and I have the alarm set primarily in decibels because these vary in what's your reference point, right? So you need a reference because in electrical signature analysis and current signature analysis, everything is from up here down. So this obviously is vibrating in the other room, about 300 feet away. So in any case, that's the low frequency, high frequency, and I can open up voltage channels and everything else that I want. Yeah, so there's the firing frequency, about 2 kilohertz, all the noise from a VFD. So we can start sorting that out by putting up the power stuff. Let's take a look and see if we have any dynamic eccentricity. So anything that I need to do, I can still do here. You see lots of noise going on because I have not tuned the drive, I have not filtered the drive, and I set it up deliberately to be nasty. There's my harmonics. Wow, I had no idea. Interesting. Some weird harmonics in the high range. Wonder if the drive's failing. And then this is torque and also loss calculations. This is raw torque. Okay, so that's the frequency and that's the other. And then I can print a report directly out from here. It's about 7 pages. Okay, so let's turn off the data collection. Yes, I want to quit. And that's about it. So also what's happened the past week, and we talked about acoustic imaging before. Well, next week I'm going to get into RCFA stuff, but the acoustic imaging experience last week, we went out to a site and we were looking at stuff, and I just pointed at a fan that's not electrically operated, and it gave me data. It told me that I had corona, which it just was a raised noise floor from turbulence from the fan. So that went along with what a military group told me about detecting stuff before opening a door. So what we did there is I use infrared. So we wore the gear we're supposed to wear. I'm not going to rely upon something I hold up to a door to determine whether or not I wear protective gear. I'm going to wear that protective gear. Then I'm going to open up the door. Then I'm going to go in with infrared and look for loose connections. There's nothing more fun than holding a wire. And then we clamped onto the data and everything else. But what we did notice, and this is one of the things that I like about electrical signature analysis, is nobody pays attention to the connection boxes, whether it's energized or de-energized when you're hooking up for test and following whatever rules are appropriate for that particular application. It's the ability to see problems. And I'm going to talk about some electrical reliability stuff next week, I think. Partly RCFA stuff. I'm going to show some horrible pictures of what can happen, what can go wrong. All experience from, 3.5 decades of playing with this stuff. So we will see you next week. I hope you enjoyed this video and my little complaints, and let's see if this one worked. Have fun, folks.